Okay, sir. We'll wait, sir, another 5 minutes.
Okay, so start it. Okay, any doubt? Somebody raised a hand. Okay, so what we will do today, because from day one we have shown that some major blocks that are required to do a design of any bigger system. So we discussed what are the blocks we discussed. First, we discussed one adder subtractor. Then we discussed one multiplier. Then we discussed subsequential blocks like register. Then counter. Then I discussed one block called general delay, memory. So all these blocks I have shown you that how to design these blocks and simulation also I have covered in my previous session. So today, as I have already told you, I'm going to show a simulation of exponential block. And what we will do by this basic block, we'll try to implement this exponential block. We are going to verify the exponential block, and after that, we'll implement this exponential block and try to find this design performance. Okay, so these things we'll try. And I was then, if I have time, then other questions also we will discuss, like how to access a memory with a counter, how to give input from the MATLAB. These things we will discuss if we have time. So basically, I will try to design this exponential block from scratch. So like basic with the basic blocks. Uh, I hope many are not following this kind of techniques because they want to follow, they want to use the model-based designs. Some are very handy with IP blocks, but sometimes if we need a custom block, that time we need to use this kind of basic block to design one subsystems in our uh, design. So we'll start with the exponential block, and I told you that we will use Verilog, and with Verilog only we'll try to implement this. Okay. So yeah, I have not shared the screen now. Now I'll share. Okay. So my screen is visible to all of you.
Yes, sir, it is visible.
Okay. So during this session, if any kind of question you have, any kind of doubt you have, anytime you can ask. So I will be very happy to clear your doubt. So I'll show this slide again. Not all thing I'll discuss. I'll discuss the last part. So we're going to design the exponential block with the help of Taylor series, and this is our theory. And we explained that this way we can do the design. Okay. So we also discussed this is a possible architecture. This is yet not verified because yesterday only I have drawn this block. So today we'll see how to verify this block. And we also have seen constant multiplier, wire shifting, constant block. And finally, we have seen that because we need the exponential for positive as well as negative, so we need a select line here that will control the adder to do the addition as well as subtraction. Okay, so this is our target architecture. So first of all, uh, what we will do, we'll go to Vivado. And Vivado, I have done many things here. I close this and start with first. But this everything I will. I will delete these things. So we have started with the basic designs that I will gain. Okay, so first thing that we will do for any FPGA implementation, as I told you, we'll do the settings, we'll choose the correct FPGA port. Okay, that part I'm not showing. So first thing, what we'll do, we'll create a new source and we'll give as a name Expo 1, some module name I'll give. Okay, this module name I have given. Now, in this exponential block, Expo 1, so I will make it as a top mode. This is my first job that I will do. I'll make it as a top module. But this is going to our top module. And in this module, what I will do first, previously we have designed some blocks. Those are in this here. Yes, yesterday also I have shown you this block we have discussed. So what I will do first here, one by one, all the blocks I will copy paste. Okay, like adder subtractor we have designed, multiplier we have designed. So multiplier, adder subtractor, all these blocks I will one by one copy in my design. So that why I am comfortable in doing this, because all the file will be in the single uh, Verilog file. You can have separate also, that is no issue. But I feel like it's good to manage the designs. So I will uncomment this. So now we have add a subtractor. I have multiplier. Then what we need? I need one register. I need one register. So I'll copy one register. Okay. Next, I need one. Yeah, right shift block. This right shift block very very important. So right shift block I'll copy here. Then I will copy this general delay block, because I explained that general delay block why it is required to achieve the any number of delay by 2 clock period, delay of 3 clock period, anything can be achieved by general delay block, and you can delay any word. Okay. Then what block we need? We have multiplier, we have adder, let's say shift block, region. Okay, fine. So now uh, exponential block is our ultimate target to generate. Before that, what we will do, because we have seen that major block in our exponential is that scaling by 3. That is the x divided by 3. That block I will try to design first. Okay. So X by 3 block, I have shown you yesterday how to design. One diagram also we have seen yesterday, and that block only we will try to implement here. So write a module here, module. We can give at scale 3 and the parameter, sorry. So give it a name, give it a parameter. So in this main block, what are the input maybe possible? Possible is a clock. Clock we have to give, reset we have to give, input should be your X, and some output should be there. Okay. Then we'll do in the module. Okay. Then what are the inputs we have? We have clock, reset, and we have input. Input is 0x. Output is okay. Now, while doing this kind of exercise, I may do some mistakes. So, if any mistakes, if I do, please let me know. So now, to achieve this scale 3 block, we have to see the main architecture. So what I am following here, I am following that the basic blocks like adder, subtractor, counter. You can implement by with the help of either behavioral technique or data flow or structural anything. But while doing the some higher blocks or higher sub blocks, I am following a structural technique. So scale 3 uh, module, I will try to design using the structural Verilog technique. So follow these. I need to again see the diagram. The diagram is very, very important to see here. So diagram I'll open here again. So this is the diagram I modified. So modified means diagram is same, but here one changes is there. Changes is that in that diagram, if you see all the wires, intermediate wires are put. If you see here, after RSH 2, 4, 6, and 8 block, there are some wires called T0, T1, T2, T3, T4, T5, T6, T7, and finally we got A by 3. So this uh, wires we should define. Okay. Now, oh, before anything, I should tell that I am going to implement this exponential block for precision of 9 bits because yesterday I have shown uh, for 10 bits. So because this block is already available here, so I don't need to again modify this block. So I'll go for only 9-bit precision and I follow this block only. Okay. So now, so our input is X and output is Y. So what is the blocks I need? I need RSH 2, 4, 6, and 8. What this block do? They just shift. So first of all, I'll call the RSH block. Okay. So RSH block here, this is the block I have for RSH. That was right shifting. So copy this and directly copy here. P is number of bits to shift. Okay. So give here n. How many bits I need for the first one? I need 2 bits. Put it 2 here. Give it a name, sh1. Okay. What is the input? Input is x. What is output? Output is t0. What is rm? Now rm is the residual. That's why, or remainder, we can say. So remainder, I don't need. Okay. So I will ignore this output, not required. Okay. So now how many RSH block I need? I need total 4 blocks. You can simply copy here 1, 2, 3. Okay. So now I can give the name 2, 3, 4. Okay. What is the output of second block? T1, T2, T3. Modify this block also. Shifting required by the second block is 4 bits. So then 6 bits. Then 8 bits. So done. Shifting part is done. What is the next step? Next step, I need one adder. Okay, I need one adder subtractor block. I'm here on the adder subtractor block. Copy this, put it here. N give us AD1. Now, what is the input of this adder? Is T0, T1, and this T output is T4. So T0, T1, they're connecting together and output is T4. And select line. Now, this adder will behave like a only adder on we require here. We don't need here subtraction. Okay. So as we don't need subtraction, what we will do, I'll put a constant value. One tick p 0. So that means it will perform always addition. I don't need subtraction here. This select line for this adder subtractor will be always 0. Then I need another adder to add other two inputs. It will be AD2 and input here is T2, T3. It will be T2, T3, T5. Done. At last, what we need, I need two register. Register also I can copy from here. It's already there. It's called register here. So I'll put it here, one register and another parameter, range one, any name you can give. What is the input of the register? So right hand side is the input because see the sequence you should very carefully see. Here I follow the sequence of the first right hand side is the input and left hand side is the output. So the sequence is very important to maintain here in this kind of structural technique. It is not positional. Uh, it is positional actually. So what I will do here, I have to give input correctly here. Input is T4. What is the output? Output is here T6. Okay, done. Next, similarly, I need another. That is T5 is the input. T7 is the output and range 2. This is the final and last stage. I need one final adder. This adder is very important. This adder is last stage adder. Here I need to add T6, T7, and finally we get T8. Okay. So all the as per the diagram it is completed. Okay, as per the diagram we have actually written all the words and all the values also. If any mistake, please try to see here, try to identify any mistake. So here see block name of all the RSAs should be different starting from SH1 2 3 and 4. Error subtractor name also should be different, AD1, AD2, AD3. Register name also should be different. So no instance should have the same name. All should be have different name. Okay. Now it is showing some red color underline. That means it is having some error. What is that error? Error is that I have not defined the where. Okay. So the where I have taken here, it is actually of 2D array. So I will take it like this as a where n minus 1, 0, t, and how many where actually I have defined here? You will see 8, 8 to 0. So I will write here 8 to 0. Okay. Now all the red lines are gone here. Now here one thing I have not done here. I have given here T8, but output is Y. Why? This I have done because after adder also I want to put one register that is not shown in the diagram, but I will put one register here in the uh, sub block only so that in the main design I don't have to put any kind of register. Okay, so what I will do here, I will put this register again after this adder. It will be register 3 and it will be your T8 and finally we'll get here 1. Okay. So till now, any kind of doubts if you are having, please ask because till now we have completed the major block that is scaling by 3 or you can say constant multiplication block. by with the help of shift and add. Anyone? Any doubt? If you are attending, please try to understand that we may do some mistakes while doing, and if you can check this errors, it will be very, very good. So I have no doubt till now. So we can proceed to the next thing that is called the main design. Main design we will do now. Uh, I hope there is no doubt now. Let me see. Okay. Okay. Yes, correct. Need to declare T. So I have declared it. Now it is fine. Okay. Now we will mm, proceed to the next block, that is main design. So I have written already here Expo 1. Now we will start. So here also, if you see, uh, now we start the main design. So in the main design, what will be the inputs? Input again, some inputs will be common, na? So I'll copy entire this part from the scale block and copy here, paste here. Okay? It will save time. Delete this. So in the main design, what will be the input? Clock, reset, X and Y. Okay, this will be the final thing. Okay, now this also common, also will be common. So basically, I am doing this exercise by doing block by block so that everything you can understand. Okay. Okay. So next is now next block I have to show here. Uh, this is my main block. Okay? So x by 3 I have done. What is the next step? Next step is that I have to uh, achieve the x by 2. How to achieve x by 2? Because again it will be right shifting. Right shifting block I need to find. Right shifting block. Right shifting block already I have used in this scale block. So I'll copy this and paste it here. Now scale block I need to copy from here. It will be scale block. So here I need to delete this. I need to delete this. It is scale, given the name scale, it is the shift. So okay. So input is X. Now, what is the output of the scaling block? It is I have given here T0. Okay. What is the output of shift block? Is T12. Okay. Done. But one thing is mistake here. RSH wired shift block. Uh, if I need to divide any number by 2, how many bits I need to shift? I need to shift it by 1. If I want to divide it by 2, I need to shift it by 1 bit. So I have achieved this x by 2. So I write here it is actually x by 2, and this one is equal to x divided by 3. So I have done 2 blocks, and third line directly going to delay. Okay. Now, okay. Now what block I need? I need one block that is called adder. Okay. So I'll call this adder block here, adder block. AD1. Here select, I'll type it as a select. What is the input is T0 and 1. Okay. So 1 plus T0. So I write it here tick T512. Now, why it is tick D512 means 1? Because I have used 9-bit precision. I am taking as 9-bit precision. Okay. So that's why it is 1. Okay. So tick T512 is equal to 1. Okay. So 1 plus it is 0. What is the output? Output is your T1. After that, I need to add one register. To add one register, register. So what is the input? Input is T1. Output is your T2. Then what I need? I need a multiplier. Multiplier register. I need one multiplier. Multiplier I have here already. Take one multiplier. Multiplier. Okay, multiplier I need here. One. So in the multiplier, what is the input? Multiplier is a T2 and T3. Okay, it will be T2, it will be T3. What is the output? Output is T4. Output is T4. Then I need another register. What is the input to the register? It's T4. So T4 is the input. Output is T5. Then what I need another adder. In that adder, what is the input? It's a T5. What is the output? T6. Then I need another register. What is the input? T6. What is the output? T7. Then in another multiplier. In this multiplier, what is the input? T7 and 11. So it will get T7 and T11 and T7 T11. Finally, output is T8. Okay. After multiplier, we have another register. So T7, T11, T8. So T8 will go to here T9. And finally, we have final one, another adder. That adder has input called output called T10. Input is T9. Okay. And finally, we have last register here. This register has input T10. Output will be your finally you get Y here. Okay. So almost done. Now all the adder subtractor are placed, but I have to see that their name should not be repeated. So how many adder I have used here? One, two, three. All the adder names should be different. So here 81, 82. Last is 83. Then I have two multiplier. Multiplier name is M1. Here it should be M2. Register name. Okay. RG1 should be RG2, should be RG3, should be RG4, last is RG5. Okay. The entire this data path is completed, but what is missing here is that this delay line. Okay? So before starting with the delay line, I must tell why this delay line is important. The delay line is important here because that if the T0 watt is reaching to the adder and this T2, let's say T2 is reaching to the multiplier, at the same time, your T3 also should reach at the same time. That's why I need to delay x by 2 by the same amount where this scale block is having. Let's see what is the delay scale block is having. So if you see the delay, number of delay the scale block is having is here, one register. This register is having one clock cycle delay. And after this adder also we have placed one register. So total delay is two in this block. So two two delay inside the register, inside the scale block. And also, if you see, there is a register placed between this multiplier and this adder, multiplier and adder. The total delay, if you can see, there is 3. So I have to send this x by 2 only after 3 clock cycle delay. It is mandatory. If you are not sending, then we'll get wrong answer. It's called pipelining. So each line or each path should have same number of delay. Okay, it's very, very important. So here, to have that delay, what I will do, I will start that general delay block, this block. I will copy from here and I will use in my main design. So, okay, now, so data width is n. That means what is the data width? And D, second number was D. That is how many clock cycle delay you want to achieve. So 3 I have given. So achieve 3 delay by this block. Name you can give delay 1. Clear? Any doubt? So this block will delay the x by 2 by 3 clock cycle. Okay. What is the input here? The input is x. And as per the diagram, output is around t 12. Clear? Okay. Now, if you see in this multiplier, T7 is one input, another is T11. So T11 or 7 also should reach at the same time to this multiplier. Otherwise, we'll have some computation error. So, so can you calculate the delay here? What delay it should be? If you see easily, you can calculate here that up to this multiplier, we have 3 delay. After this, we have one register and another register placed here. Total delays, can anyone tell what is the delay amount we should place for this X? Anyone? Anyone can answer? What is the delay, amount of delay we should put for the X? It's very important to have the same delay for each signal. So, no answer? Okay, so again, I'm trying to see this. Up to this multiplier, we have total 3 delay, as I have seen. And after this part, we have total 2 delay. This one register and this one register. So total delay, we have to delay it by 5. Okay. So this signal, this the delay block, again I will copy here and I will put it here. So name should be different. So X is the input signal, output is T11. Let me have T11. So now see, everything is completed now. We have delayed the signal, also connected here. So what is pending? Yeah, I have not declared the where. Okay. So how many where I have used? Let me check. Here maximum I have used T0 to T11 through 12. So I write here what is the where? Where will be n minus 1, 0, T will be 12 down to 0, done. So any other mistakes if there? What is a mistake? It is there. Uh, okay, can anyone help with the mistakes? This is very, it's very important. All the mistakes we should try to understand, and then only it will be possible to have this. So here, select line is not declared. I've declared here what is select, clock reset, select. Okay, this is done. Then what? Here, So here kind of mistake is there. Yeah, we have double bracket here. This is one mistake. Here also I have double bracket. This mistakes we should understand. So now I see that this design is very uh, fine, and we can see that there is no error left here. Now, what is the step? What is now? I can move to the uh, verification of this exponential block. All the blocks I have connected. So for verification, what I will do is that I have to write some test bench. For test bench, I'm not showing how to write because test bench I have already have written, and test bench I told you is very uh, test bench I have written here. Test bench some. So what is our main design? Main design is that expo. I have to call it here. Expo is the main design. Okay. Initially, now one thing is very important here to understand that how many bits do I need to design this exponential? Because precision is 9. If precision is 9 bits, and we also know that inputs of to the exponential block should be 0 to 1. Okay, we know the input range, we know the output range also. Okay? How we know the output range? Because if we see what is the maximum possible value of the output, so we can see exponential at 1 because input can be maximum 1. What is the maximum output possible? Is 2.71. Okay, maximum value possible is 2.71. So how many bits we need? 9 bits are for fraction. Okay, and 2 to represent 2 is the integer here. So to represent 2, I need 2 bits. So 9 plus 2, 11. Now uh, to have the signed and unsigned difference, I need one more extra bit. Total number of bits I need here is 30. Okay, total number of bits I need total is 30. So 9 plus not 30, 9 plus 3 is 12. 12 number of bits I need. So we need 12 number of bits maximum. If 12 number of bits I have, I can design this block. So 12 number of bits enough. I should not use more bits in this design. So that's why I have written output width is 11 to 0. What is the input width? Input is also 11 to 0. What are the inputs I have here? Clock, select, and reset. Start is not here. X, not X, X. Okay. So I'll give first input. Start is not here. Okay. So again, I'm telling that so my clock period is 10. Clock period is 10 nanosecond. Initially, clock is equal to 0, and every time in a sequential circuit, reset should be 1 initially. Okay, reset initially is 1 to get the 0 value at the output of the resistor. Okay, this is very important. So I have select start. I am not using as of now. So start, I'm commenting out. What else I have pending here? Export defined, select defined. Okay, initially I check for positive value of exponential. That's right. Select is 0. That means all the adders in the main design will behave like a adder. That's why here select line is 0. Clear? So now we'll go for a simulation. Input X, this is a mistake. Input should not be 17, it should be 11. Okay. So input should be 12 bit, output is also 12 bit, and 9. 9 is the precision. This is the precision. Precision is 9 bits. Okay. So now we'll go and let's see here. Exponential T is already top module, so I can do this simulation. Okay, let it simulate. Okay, now you can see there are some mistakes. I mean, in the code, maybe because red light means there are some mistakes and the result is not coming properly. So the result is not coming properly. So what do we do? We have to investigate that why the result is not coming properly. So for that, what I will do that a troubleshooting method we have to apply that up to what level my output is correct. Up to what level my output is correct, that I have to check. After that, one by one, we can investigate that what is wrong with the code. For that, what I will do, I'll go to scope. I'll go to scope and there I go to unit under test. Inside that, I will check that what is the first block I have designed. First block that I have designed is scale 3, that is divided by 3. This block I'll keep. So scale block I'll check first. So scale block, to check the scale block, I'll go to object. So here, if you see, scale block is only the mistakes I have in the problem in the scale block only. Why? To see, input X is correct because it is showing correct out correct input. All the wires are correct. All the wires are showing some value, but output is not showing proper value. Somewhere it is having mistake. So we need to go back to the scale block again to see that what is the error it is having. Okay, so I will go back to the scale block and check that what is the problem it may have. Okay, so it looks fine. Input X is okay, fine. Let me check. Okay, if you can identify any error, please also tell me because sometimes we do silly mistakes and we search for other errors. Okay, you can compare to the diagram also that what error we may have done. Okay, so first is user output is T0, T1, then T2, T3. We have added T0, T1. Output is 4, 5, T2, T3, and T4 going to T6, T5 going to T7. So we have T6, T7 adding T8, T8 going to output. Everything seems correct, but still we're not getting the output that we have to check now. So okay, so what I will check here, I'll go back to scale block and so this I am doing so that you can also have some troubleshooting idea that how to do troubleshooting. So now I have added all these wires in the design. You can just simply restart it and then run for some time. Okay. Here you can see that which wire where it is having. So all the things are correct. All the wires are showing correct value. I have some problem in the Y. It's having some mistakes here. Okay. Once again, if you see the code, which one, two, three. Okay. Okay, now the better way to understand what is the error we have done. Sometimes we are not understanding that it looks no problem in the scale block, but it may have some problem in the main design as well. So to understand that, what we will do, I will select this block as a top module and I will synthesize this block. Okay. So better understanding can be done by doing this synthesizing again and again. So I will do synthesize and there will be some issues, warnings or error it will show. And based on that, I can also find the error. So it is again we look for the code that it may have some error. Okay. Implementation we're not doing as of now. We will check for some errors here. What messages is came. Ah, see, one error came that is very critical here. That it's showing that line 95 multi-driven NAT on PNAT in 17. That means we have done some mistake in the connection that somewhere it's having output at two times. So, okay, here what is the error? We can have here. So it's clearly showing some error we have done. So once again, we will match all the connection here. So scale block, if you see, just a match with a previous written diagram here. So here, if you see, scale 3 block has output x t0. Well, let me check the sequence of this block also, x and y. So here t0 is the output, that is correct. Shift block, first wired block are okay. The mistake we have done here in the RSH wired block. Okay. Here input is x by 2, input is x and output is T12. This is the mistake we have done. See, this is also on one learning that one wire cannot be output of two. This is a very important that one wire cannot be output of two blocks. So here one mistake I have done that output should be T12 and residual we have already ignored. I don't know why this mistake I have done. So output should it's already removed to see in the scale block. So output is removed. Now that remainder is removed, and we have input x, output is input. Okay. Now again, what I will do, I'll again do the simulation by closing this simulation. So what I'll do this again, run simulation. Okay. Again, I got some error in the. So again, I'll go back to the thing and I'll check what error I can get here. Scale block. See now scale block has actually no error. See here, scale block has no error. Okay. Scale block error is clear. Now, what is the error that here I'm getting that I'll check now one by one. Shift block is shift block has some issue. Okay, that is fine. And delay. So mainly shift block still having some error. And other than that, I have Okay, so I'll again go back to this design and I'll check that what error it might have. Okay, so to check that, I will again go back to this shift block, and in this shift block, I directly check entire wire in the test bench, and I'll do the simulation, and we can see what kind of error it may have. Okay, RM I am not using. I not using the what is input? Input is here. Input is 200, and I got mistake in 9 and 10. It's okay. Another mistake I have done here in the delay block that I'm just here I have done the mistake. So again, what I will do here, uh, I will just again open this diagram and I show you that. So here input is T12, output is T3, input is X, output is T11. So first delay block, I did the mistake. The first delay block, if you see here, input I have given as X, output is T12. This is wrong. So input I have to give here T12 and output is definitely it should be T3. And second delay block input is X, output is T. So this mistakes we have done here. So now it is corrected. Again, we can go for this simulation. Now, if you see all the errors are gone and we got our expected result. Okay. Now see, input is 200, output is 555. I think you're understanding, I know. But for that, I have to change radix, signed decimal. Now, we have used 9 bits for fraction. Okay. That means 9 bits for fraction means 2 to the power 9, 512 is equal to 1. Okay. In the TV, if you see, this is the representation of uh, 1 in the binary. So here you see 9 bits are in the fraction, 9 bits are in the integer. So this is exactly your 1. What is the value? Value is 512. So 512 is equal to 1. Now what is the output I got? Output I got here 1365. Okay. So 1365, how do you understand this? This is result is correct or wrong? So I'll go to MATLAB. I'll check what is the result for exponential. One result is 2.71. Okay. So in Xilinx, I got 1365. How to understand it is correct or wrong? What you do, you just divide this output 1365 by 512. 1365 divided by 512 is exactly you will get 2.66. So your correct result, what you got is your so result you got 1365 divided by 512 is equal to 2.66. What is the actual result? Actual result is 2.71 versus actual result is equal to 2.71. What is the error you're getting? Some 0.05. Okay. The error you are getting 0.05. Okay. So till now, any doubt? Because after a lot of errors, we got finally the correct result. So if you have any kind of doubt, please tell me, or any kind of query. Anyone? Anyone? If you have any doubt, please tell me because simulation is done. Now we'll go for other things. So it's a completely I have shown using the structural coding how we can build the design. Maybe it will take some time initially, but once you do practice, then you will find that it is easy to do this way. So if you have any doubt, please let me know. Now we'll go for next step. So the result that you got is correct. Now, what we will see that you may be asked, you may have some doubt that okay, I have shown only for one value. Okay, let let me show for other value as well. So this data is exactly zero point 0.5. Okay, because it is after decimal point, it is 1, so it is zero point 0.5. Let me check the value again. Open this untitled 22 and relearn. So now you got two input, now you got two output. And the next result you got is 842. So again, divide, check what is the result if you got. So actual result here, first let me check actual result. The actual result, what you will get exponential of 0.5. You will get around 1.64. You get around 1.64 in the actual value. And what you got is 8.842. 842 divided by 512 is 1.64. Okay. So 1.64 and almost it's actually almost correct. Slightly we have less value. So this way you can get the correct value of the exponential. Now only positive we are calculating now. Okay. What about the negative? If you want to get the negative value, then what we will do? We have to do the select line change. We can make it 1. Okay. So if we make it 1, all the adders will become now subtractors. Here in this diagram, see, we have a control line which is select in our case. If this is 1, all the adders will become subtractors. Okay. Yeah.
Me and
Somebody has
Gulshan
any
both
question?
will fight.
Yes. Yes. What is the question? If you have any doubt, please ask.
I before Wonderland.
Yes. Do you have any doubt, Saipavalika? Okay, then I'm waiting her. Okay, so we proceed to the next session, next topic. Okay, so now we'll go for this negative exponent. So if you see here, for negative exponential, I have to make this control line 1 so that all these adders will behave now adder subtractor. Okay, will become as a subtractor. So I'll make it 1 here and this code again. Okay. Now we see whether it is giving the correct or not. Okay. So I got two value. First one was minus first 171. It is corresponding to the power. So first the value e to the power minus 1. What result I should get here? Minus 367. 367 is the result actual. I got here 171. Is it correct? Again, check here. 171 divided by 512. Yes, almost. Uh, I am getting 333. It is also correct. So now we can check the next result. Next is exponential minus 0.5. You get it 0.6065. What we got 309 divided by 512. Yes, exactly. It is the same value it is showing. So we can say that our design is functionally verified for both positive and negative numbers. Okay. So design is almost functionally verified. I can say it's functionally verified. So rest other verification can be done later. But as of now, you can say this design is functionally verified. Okay. So if you have any questions, tell me. After verification of this design, we'll go to the next step. Anyone has any doubt except Prabalika? She's raising her hand. Anyone? Okay. Now what we will do that some error we may got here, but what is the reason that we are getting error here? The error we are getting because firstly we are using the Taylor series. It is approximation only because it is not the exact because we have removed some terms. We have only considered how many terms here? Three terms, I guess. Uh, in main, we consider only four terms. 1 plus x by 2 plus x by 3. So only four terms are considered. So you'll get definitely some error. Then the second is that precision. We have chosen precision here of 9 bits. So definitely you will get some error. If we increase precision, then definitely you'll get better result. But if you increase precision, your hardware will be so precision you are increasing, order also more. Okay. Then how to measure this accuracy in terms of other matrices like RMSE is very popular. Then RSNR in DB or simple SNR also you can put. So RMSE, RSNR, SNR. Generally preferred is either RMSE or RMSE in terms of value or RSNR is preferred. RSNR means relative uh, signal to noise ratio. It is very important. So by this matrices, you can measure the what is the accuracy of the design. Okay. Okay. So now our exponential part verification is done. Now, what is important thing that I want to show you that in the last session also I have observed many were asking questions that how to give input because I have given here all the simulation input only means all the inputs I have given through simulation only but how to give input to this exponential design so in other way suppose I want to use this block in some network okay so in that case what I will do uh, I will give this input through some memory. So what I will do, I'll store some value in the memory, and through memory, I will give you the data to the exponential. So I'll write another module called module expo test. Okay, and this block I'll use for testing. Okay, this block I'll use for testing, and now I'll store some value in the ROM, and this stored value will be fetched by some counter and given to the block, exponential block. Okay? So this block I'll call in this block my precision, precision, and so now I'll call this. But how to call this? For that, I have to design some ROM. Okay? Design some ROM, and I need some counter. Okay, so I'll fetch the counter code, which I have already done. Here I have done some code here. Yes, this three code I'll copy here. I'll explain a little bit about this code also. Counter, I guess already I have shared. Okay, first block is PGBH block. This generally I have used in my design. This PGBH block is not a big deal, not a big module, not a very important also. So this block, PGBH block, what it does, it receives a pulse called start, and based on this start signal, it generates one phase, this Q, and whenever another pulse called stop comes, this enable signal becomes zero. This is a kind of a, uh, I can say, phase generation block. This is a phase generation block I can use in my design. So why phase generation is important? Because I want my design to be of low power. So if I want to be low power, I need to stop the modules after some time. That's why I need some block that will generate the phases, and also it can stop the phases. This block I generally use. So it's very simple behavioral coding I have written for this block, and I will use here. Counter, and this memory block I just show you how I have written. It's very simple. That always have this positive clock if enable read. Okay, is out a, and it will take the initial value from the initial name.name. This file is important, initial. From this file, it will take the initial value. In which format? Binary format. Okay. In binary format, it will take the value from this file and put it in the this 2D array called mem. Okay. And this ROM I will use here. Now, what I need this initial file. Initial file already I have prepared somewhere. This file. So how to prepare memory file? Last day I have shown. So here I put this value. I put only four values. Okay, four values I put. So how many bits I need? I told you already that I need only 12 bits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this 12 bit I need, but this is not exactly one, I guess here. If I push here, this is what should be my bit. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9. So this is my, I guess, B. So this is now, first is 1, second is 0.5, third is 0.25, fourth one is 0.125. So I have given this four values. It will go to the memory, and to call this memory, I have written some code initially also. That code just okay. I can write here also by directly. What I'll do. So I need one memory. First, I need one memory. This I will put it here. This is your N. And what is the width of the memory? It's a 2 bit. What is the name? You can say name one. Now, what is the output of the memory? I need the output to be X. X is the output. That means this X will come from this memory. This X will come from this memory. So I no longer this X to be input. I'll convert it to Y. Okay. Now I need some counter to read this X values. So I need a counter. I need a counter here. I'll give a counter here. Counter. So how many addresses we need? I need because memory is only have 4 locations. So I need here also counter 4 locations. That is for count address. Address output of the counter will be ADA. So this address generated by the counter will go to the memory. So it will be 50 and TC. So counter we have discussed in the last class. So terminal count signal it will generate. This signal only will be used to load this counter and it will generate some enable signal. So is enable and this enable should be same. Okay. Now I need the last block called phase generation. This block will help to generate this. So PC block will be used to generate the enable A signal. So I will use some start signal and PC will stop it and enable A signal. So this start signal will generate the phase enable A. This will go to the counter as well as to the memory. Okay. So now I need a pulse called start. Here also one start I'll put. Okay, so now it is done. So what mistake I have done here is that X is not used. So I don't need this X because it become now as a wire. So now this entire part, actually I can comment that it's actually reading. Okay. So now the setup is done. Now limit I have to say, what is the limit I should use here? What is the maximum count? Is 3. Okay, that is counter will count up to 3 only. There are some errors that the where I have not defined. So every where you have to define. This is very, very important. So TC, now everything is TC is defined or defined. Enable is defined. I will define this where 120 ADA. Then X I already defined. Clock this side, clock this thing X select is already there. So everything I have actually defined. So now what I will do, I just simulate this test bench. I have to modify. Okay, I have to modify this test bench. I have included one start signal. 1 second. Okay, sorry for interruption. So here I have given the start input here. So this entire thing I have to call again. It's for test and start. X is not there now. X clock start Y. So start Y. Start now I will use. It's very important. The start is initially 0, then become so now see, I don't need this to give this x because x is now coming from the memory. Okay, I have to give only this start pulse. This is the important thing here. So now in the entire this design, I don't have any input, any input vector. I have only all these single bit inputs, clock, reset, select, and start. Start is the main signal that is starting the design, and Y is the output. Okay, so now it is defined. Now I can so range X is also not required because there is no input. All are like that. So now I will see this bench again. Okay, now I can simulate again. Now here, if you see, I got some values here corresponding to the uh, input. What are the input that I will show you first? So go to go to objects. One second. So output is coming, but I have to show you that what input is coming from the memory. For that, you go to scope, put again UUT, and then select the X. That is X is the output of the memory. Also, you can select the address, enable, PC, everything. So take it in the test bench and make this as unsigned XML and run for this 10 microsecond duration. So if you see here, your address is 0123, and during this duration only, your enable signal is on, active. That's why I have used that phase generation clock. I don't need this counter to run for a long time because it will give you a high power in the implementation state. And this terminal count signal is very, very important because based on this signal only, I have stopped that pulse phase. Okay. So the inputs from the memory came that 512, then 256, at 128 and 64. That is 1.5, 0.125, and 0.0625. So based on that, I got this. Okay. So now entire this simulation part is done. So what is the next step? That is you have to check in kind of FPGA implementation. In that already, I think many of you know. But I should tell you that after simulation, I have to go for the implementation result. That what implementation it is performance it is giving. Okay. So I have chosen here one basic Spartan 7 board. Spartan 7 board I have chosen. Based on that Spartan 7 only, I will give you some design performance. So, but before that, if you see here, so many blocks are here. I should delete these blocks because redundant blocks should not be there while you are doing the implementation. Okay. So, what are the steps in getting the implementation output? First is you have to do synthesis and then implementation. Okay, these are the steps already we know. But before going to these steps, also we have to add the constraint file. That is for the FPGA, which connection. That's how the output of the design will be connected to the FPGA pins. That is very very important. That I have actually prepared directly I will add that. Uh, I have prepared somewhere. Yeah, it is there. Okay. It is there somewhere. This I have prepared. So we have total 12 bits output. So 12 bits we can easily give to 12 LEDs. 12 LEDs we can easily give. So 12 LEDs I have connected here. So if you see clock, first connection is clock. Clock should be connected. Then select. Select generally we should give by uh, through the switches because it's a select line. Is like I have given in the switches. Then I have chosen the LEDs for the output. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. Okay. But here it is 13. So I need to delete one. I need to comment this 12. So up to y0 to y11 are required for my exponential function. Then reset and start. So reset and start I have declared through the push button. Okay. So reset and start through push button and select from the switches. Okay. This I have given here. Now, mm, now everything is done. But initially, I will not implement on the hardware. Before that, I need to perform the implementation thing, and performance also I have to obtain. So for that, what I will do, I will uncomment this line. This line is very important. Just that it is saying that okay, use clock period of 5.5 nanosecond and duty cycle of 50%. So your clock period is now 5.5. Okay. So make it round figure, make it a 5, make it a 2.5. Okay, clock. So now what I will do based on this constant file, I will synthesize my design. So make synthesis. Let me check this top module or not. Is top module to synthesis. Okay. Now this process will take some time. So in this in between, if you have any question, please let me know because some time it will take. Then only we can obtain the design performance. Okay. Uh, Run implementation we are doing now. I forgot to unmute. So run implementation we are doing. Uh, so after run implementation, we'll get some implementation results. Okay. And these results are very important for our writing papers. Okay? That means what performance it is giving based on the FPGA board that we have selected. So we have selected one small board called Smarton 7. Okay. Now that we'll check it is completed or not. It is still doing some error is given. What is that error? Then again, we have to find out that what is the error it is giving. Many kinds of error it is showing. Okay, it may be showing that some of the output that we have selected, the LEDs, is not matching with some of the inputs that we have to check. Okay, so it is that error only. So what we will do here, we will initially, okay, okay, we don't need this thing as of now. What I wanted to show actually that let me first concentrate because you know this thing already. What I want to show is that uh, again we will do this implementation part. So basically, I want to show you one important thing that is the FPGA implementation part. Uh, uh, that B-stream generation I am not doing that you can do because uh, already known process how to generate the B-stream. But what is important is that how to find the FPGA performance and how to optimize. That is very important. What are the parameters we should target that we should know? The first parameter is that accuracy. Accuracy we have to maintain that accuracy should be uh, good. Then area we should try to optimize. Then latency also you have to check. Then throughput here doesn't matter because we want one data per clock cycle only. So throughput is doesn't matter. Latency matter that how many clock cycle later we are getting the output. Latency we will check the simulation. Latency also you can check through this design that after how many clock cycle you are getting this output. If you see in the scaling block x by 3 module having two registers here. So, so total latency will be 2 plus this block 3 plus this block 4, this block 5, then 6, 7. So you can say our latency is 7 clock cycle. Here, latency is very, very important, and many people have used Cordic, and we can say that Cordic has the highest latency in terms of computation of this exponential. Okay, so now implementation is done. What we will do, we will open the implementation result. But what is important here is that first we'll see some reports like that hardware reports that generally we get from placements. So placement will get some result report utilization. That is how many hardware you have used. This is very very important. So here if you see 56 we have used slice 0.7%, 57 slide registers. Okay, these two very important slice LUT, slice register. Okay. Next, what is important? This. So this parameter is very important. The occupied slice. Even though if you are having less number of registers or LUT, it may get a higher number of occupied slice. Why? Because your design is not that systolic nature. If your architecture is systolic, you will get less number of slice. But if your architecture is serial, like it is having feedback, then you may have a more number of occupied slices here. This count is also very, very important to show in your design performance. Clear? Next, coming to the point is that we have the DSP blocks to implement the multiplier or adder. Here you can see we don't have that much utilization of memory. Memory, why we are not used? Memory we have, it is not used because we have used only four location, and for four location, RAM 8 block, RAM 18 block memory will not be used. If it is more than like 16, uh, 128, then it will be used. But for four location, it will not use the block memory. Okay. DSP, two DSP blocks are used to implement the multiplier. Okay. So two DSP blocks are used to multiply. For adders, it is done by the mm, LUTs. Okay. Then only this much is important. Other things are not important as of now. Okay. Now, what is important more here is to design the uh, power. So this power is very, very important because what is dynamic power we're getting here? 0.042 watt. This dynamic power we have to put in our paper. This is very, very important. What is the power? But power at what frequency also it mentioned, because we have used here 5 nanosecond frequency. So 5 nanosecond means 200 megahertz. Okay? At 200 megahertz, we're getting this dynamic power. And another important thing is that what maximum frequency you have achieved. Now, I have given 5, I have achieved this frequency. But is it that maximum frequency of 200 megahertz only I can achieve? No, I can achieve more than that. So for that, I have to push little bit harder in the constant file. What I will do here, I'll again modify the constant file. I'll try to again modify the constant file, and I'll give a better target here. I'll make it say 4, and it will be 2. So again, if I do same thing, and we'll check whether it can achieve or not. If you still can achieve, I can say that, okay, my design is actually achieved that much frequency. So we have to do this trial and error process every time, and then we have to modify the circuit again. Then only you can achieve the best achievable frequency. Because what happens when you're writing some paper has achieved the frequency that you are not able to achieve. Okay, that time we have to go back to the circuit that where we have done the mistakes. Okay, so we can achieve more accurate, more frequency. We have to modify, we have to add resistors so that we can achieve a good frequency count. Okay, this is one. Also, we'll see here that at 4 nanosecond whether it can achieve the frequency or not. Let me check this thing. In between, anyone can ask any other questions. It will take some time because whenever you are trying, now this time depends upon your design size. Here it is taking a few minutes, but if your design is big, it will take, it may take 1 hour, 2 hour, maybe 3, 4 hours it will take for this process. Now see, again you will see whether it can achieve that frequency or not. See, it is still achieved this number. So you can go further and you can check that when this post negative slack or TNS is still positive or not. If it is still uh, negative, if it is going to negative, then you can say that it's not achievable. Okay. So this way, you can do the simulation. You can find the uh, implementation parameters. Okay. Now one more thing I need to show here. I'll, so I will just say here one thing that I will not perform this thing, but I'll check tell you this is important. Okay, this important thing is that we're doing some simulation. In simulation, we have two options. One is behavioral, another is post-synthesis functional simulation. And many a times, behavioral simulation does not match with the post-synthesis functional simulation. And both, if you are only doing behavioral simulation, it is not enough. It may not be implemented by the FPGA properly. So you have to perform the post-synthesis functional simulation also. Okay. Timing, I'm not telling that you have to do, but functional you have to do must. Both functional and behavioral should be same. Then only you can say that okay, my design will be implementable on the FPGA. Before implementing, also you can say that it will be implemented 100%. Okay, it's very important to perform the behavioral and functional simulation. Okay, so both simulation should be same. Next, I want to just highlight one thing that okay, you have implemented the design on the FPGA, but what now? What is the next step? How to verify the implemented design, whether it is implemented correctly or not? For that, uh, once you perform the synthesis, then go back to this setup debug. This is very important. So setup debug, here you have to set up the pins. So except clock, you have to find all the nets like reset is one of the net. Reset input buffer you have to choose. Then what you have start you can choose. Then what we have clock, we have how many clock and reset, no? So clock, start, reset and select also we have. Except clock, how many inputs we are having, that we have to find out. That is select input buffer. Then we have the output is y. So y, what is the output? Yeah, this one only. So for input it is input buffer, for output it is output buffer. And then you can select that how many points you need, how many problem stages you need. Like they generally make it default only. Then you can go back to this. The clock should be found. One debug code should be created. This is very important. After this, so here what is happening? Uh, one soft code is generated in your design. That code will try to verify the implemented design in the uh, FPGA. Okay, so here after doing this, you will get some schematic, and you have to save this here. You have to save this constant. Why? Because your constant will be changed now. After this stage, your constant will be changed. If you see here the constants, go to sources, the constant will be changed, and you'll get a modified constant file. Here it is not showing constant file because actually I have not added the other constants, but your constant file will be changed. So this is very important. Now, next thing is that after doing this thing, you can actually go back to the. So after doing this step, you have to again do the implementation, and then you can program and debug. Okay. So after that, you can after implementation of the design in the FPGA, you can check here in the open hardware manager. Here you can implementing the design, and you can also verify the design. Okay. So that's all from my side. If any kind of question you are having, please let me know. Mm, Entire process is not possible to show. Anyone, if you have any question, please ask. Any participants have any doubt? or no one followed. So I am stop presenting now. Also, you can write the doubts in the chat box if you have any kind of doubts.
Participants, any doubts? If you have any doubts, please ask. You can write in chat box also. Sir, I think no doubts from participants. Shishendu sir, am I audible?
Yes, yes, yes.
Ah,
Okay, ma'am. Okay, ma'am. So if
Thank
there
you,
is
sir.
no doubt, then
Yes.
we can close this session.
Yes, sir. Thank you, sir. Very good, informative session and nice hands-on. Thank you, sir, for your time. To participants, we will inform the next session in group. Thank you all for joining.
Thank you all. Thank you all. Thank you.